right. Yesterday I talked about propagation of a laminar, premixed laminar flame, adiabatic. There was adiabatic. Now we're going to look at very briefly the influence of heat losses. What if there is a volumetric heat loss on the flame? So the idea here is that we're going to consider this way. Oh, but I'm in too full. Okay, this is what I want to look at: extinction of a premixed flame with volumetric heat loss. No, that was in between. Oh yeah, okay. So this is what I had yesterday: the burning velocity of a premixed flame, and this is for an adiabatic flame, right? So now let's look at extinction of a premixed flame with a volumetric heat loss. Now, the volumetric heat loss can influence the burning velocity. So let's write the volumetric heat loss in this form, okay? Where this is a heat loss parameter. Alpha is in some sense a heat transfer coefficient. T is the temperature, and Tu is the ambient temperature. Now, on the burning velocity of a premixed flame with heat losses, obviously is going to be less than the adiabatic burning velocity. So therefore, let this quantity m dot be rho u vu, which is, so this represents the mass burning rate of a flame with volumetric heat loss. I've written that right here, okay? So now it turns out that now we go back, we can write the species balance equation. The equation for YF does not change because it's exactly what it is for an adiabatic flame, okay? Whereas the energy conservation equation, there's an additional term here. So this is what I had yesterday, this particular, what's here in this box. Now we add the heat loss term to the energy conservation equation, right? So now the initial conditions are again as x tends to minus infinity, there's the initial concentration of the fuel, initial concentration of oxygen, and that's the initial temperature. So again, the difference is yesterday we looked at that equation and this equation, and now we're going to add this additional volumetric heat loss parameter. Okay, all right. Okay, now I will non-dimensionalize this equation. Again, this is exactly what I had before, and there's a typo. There should be this quantity zeta. They must appear here SL and S. So let's define SL as the. I'm going to try this. SL is the burning velocity for the adiabatic flame. Okay, so that's the burning velocity. SL is the burning velocity of the adiabatic flame. So that SL should appear here. Okay. So anyways, so the zeta is now the non-dimensional parameter. This spatial variable. This is a normalized mass fraction of fuel, and that's the temperature. Now TB here, that's again the adiabatic flame temperature that appears in this formulation. Okay. Now the reaction rate is given by this expression, non-dimensional reaction rate, and it was the same like what I had yesterday. And now what's new here is this quantity pi, which is defined, which is a non-dimensionalized heat loss parameter, pi, that appears here. Okay, right. So now we define a quantity m, which is the ratio of the burning velocity for the flame with heat losses over the burning velocity without heat losses. So now it turns out, now if you look at the species balance equation in terms of these these variables can be written in this form. And if you recall last class we didn't have the same, m was 1, but that's the only difference between what I have here and what I had yesterday. And of course the energy conservation equation has this additional term which is pi times tau, and that comes in from the heat loss. So these are the two sets of equations we need to solve: the species balance equation and the energy conservation equation, right? Okay, right. So now here's a very rough, which is a sketch of what's actually going on. You can see that this is a flame, and then the preheat zone, the preheat zone is unaffected, and then this is the post-flame zone, and where there is a volumetric heat loss. And again, there's a thin reaction zone, and you can see that this is the adiabatic temperature. So the dotted line here represents the adiabatic temperature, and that's the perturbation, the decrease in temperature, the reaction zone, and that's caused by because of the presence of the heat losses. So this is the temperature profile with heat losses. That's the temperature profile without heat losses. All right. Now one can now define a variable h. If you recall, recall in yesterday this was actually 0. Because we had the coupling relation between tau and YF, so the H was 0. Yes, in the last class, but now here H is not 0 because it's 0 in this region, but in this region, because there is heat loss, the H is not 0 on that side. Okay, all right. Okay, so now again, so in terms of this quantity H, this is the equation, right? And that's obtained from simply adding these two, right? Okay, so that's the equation for the enthalpy. And again, so now these are the two equations I'm going to look at, the equation for the enthalpy and the equation for the temperature, the energy conservation. Right. Okay. So now we will assume that the volumetric, this parameter pi is very small. So that means the heat losses are small. Okay. So we should look at in that limit. Right. So now, so the temperature. So if I want to analyze in this region, okay, the temperature is perturbed. So the temperature is actually tau plus a correction that appears, and this is a plus pi z. It'll turn out that z is actually negative, so the temperature is actually decreasing. That's the expansion for tau in the post-flame zone. And now what we're going to do is integrate. So what we're going to do is integrate the equation for the enthalpy, right? From minus infinity. So if you look at this flame, and this, as I said, this is the temperature profile. Oh, I should put a dotted line. That's the. So I'm going to. So this is this part of the reaction zone is 0 plus. This part of the reaction zone is 0 minus. And this is minus infinity. Right. Okay. So the integration. Okay. The integration is from minus infinity to 0 plus. So that's the integration. Okay. So now I want to take that equation and integrate it. So so now if you can see that this is actually, if you integrate this, m is a constant, all right? So when you integrate this, it's simply a h, but you can see that h at minus infinity is 0, whereas h at 0 plus is, so that's the value of h downstream over there, okay, at that point. So the integral of that first term is this. Now if you integrate this term, again, this is the gradient of enthalpy, which is that quantity right behind the flame. And upstream, right in minus infinity, this is also 0, so that comes from integration of that. And in the last term here, you integrate that from minus infinity to 0 plus. Okay? So then the next step, what I'm going to try to do is evaluate each of these terms. And so evaluate these, and all these terms individually and plug it into that equation. So this is what's going to be done next, right? Okay. So now let's look at this H plus. The H plus, if you recall, the H was defined as H equals tau plus YF minus 1. Okay, that's what is the definition of H. So in this over here, on this side, 0 plus, there's no fuel because the fuel is completely consumed in the reaction zone. So that goes to 0 over here. So for H, you can see that in this region simply tau minus 1. Okay, so okay. Or did I do that? Okay. All right. So the h of 0 plus is which I've written here. Okay. So it's actually tau minus 1 because this goes to 0. But tau is this expansion 1 plus pi z. All right. So therefore, if you substitute that value as tau, so it turns out the h at 0 plus is pi z naught, with the z naught is the value of z at 0 plus. Okay. That's that value right here. Okay. So that's z naught. So now I have evaluated the first term. Now in the next term we'll evaluate that derivative. Okay, yeah. So okay, here. So prior to doing that, of course, I'm going to look at the. I'm going to first, prior to doing that, I'm going to integrate the energy conservation equation in the preheat zone. Okay, the preheat zone, that's the energy conservation. There's no reaction. Okay, so if you integrate that, tau is given by this expression. Tau equals exponential mz. That comes from integration of that equation. Okay. Now, since I said that quantity pi is very small, and now in the post-flame zone, I mean, this is fairly large. So therefore, to analyze the post-flames, rather than stretching the coordinates, you can introduce what is known as a contracted coordinates. So to again to make this of order unity, you introduce the so-called contracted coordinates. So in this contracted coordinates, you can see that pi is small, zeta is very large, so therefore the product here is of order unity. So that is very useful to introduce this in this region, the contracted coordinate. So now if I write the equation for the enthalpy in terms of this contracted coordinates, okay. Now again, this is only useful in the analysis of the preheat zone, okay. So if you go back and introduce this contracted coordinates in this equation, right? What you see is that this is what you get, okay. So now you can see that the second derivative term, it is of order pi. And we have already said that pi is very small, okay? So therefore, it turns out that in the post-flame zone, the second derivative can be neglected. The second derivative enthalpy is only the first derivative that contributes. So therefore, you can see. So therefore, so that you can see that the first derivative. So this, if you drop that, so that's just equal to minus tau. So the second derivative dh d tau in this region is simply tau, right? So this allows me to evaluate. So now I can, so therefore it's 0 plus, which is what I want to, I need that to substitute in this equation, right? And you can see that that's simply from here, dh d tau at 0 plus, right? And recall that that's simply d tau d zeta at 0 plus, and therefore that's minus pi divided by m. So that's what it is. Okay. So this, of course, this quantity h, again, h is it's given by this expression over here. Okay, right? Therefore, you can see that d tau is pi. So now we have evaluated. So I have evaluated that, and I have evaluated this. Now we just have to evaluate this quantity, and that can be easily done because we know that tau is given by this expression. So if you substitute that, okay. Okay, so I wrote the full equation again. So now for tau, I substitute the exponential term. Now this can be readily integrated. So therefore, it actually turns out to be pi over m. So because if you integrate that, it's exponential mz. So it's just going to be exponential mz divided by m. And if you apply these limits as minus infinity, it must vanish. At plus 0 plus, it is unity. So therefore, and then if you solve this equation, you can get this perturbation z naught as 2 over m squared. Okay, so this is the right. Okay, so now I have the perturbation. I have this, so I know how much the temperature is decreased, and it's decreased by this amount z naught, pi times z naught. That's the decrease in temperature. Okay. Now again, this should be a proportionality. We saw from yesterday. The burning velocity here is proportional to this, the square root of the reaction rate. So this is proportional to that one. Similarly, we can assume that this in a similar way we view that this is the burning velocity for the flame with heat losses. Should also be, we can expect that to be exponential of minus e over 2r with a T naught. T naught being the temperature, where T naught you can expect that to be T naught, where T naught is the temperature here. So TB is that temperature, and T naught is that temperature over there. Okay. All right. So now, based on this expansion for tau, it turns out that T naught is given by this equation. Okay, where we already know what Z naught is. And now I can so I can simply take the ratio of SL or VU over SL, right? VU over SL, which is M, is given by this term, this expression. Okay, E over R, 1 over T naught minus 1 over TB. And now we can expand this in the Taylor series expansion, 1 over T naught in terms of Z. Okay, and if I substitute this over here, of course the Zeldovich number appears. So this is the final result. So the final result is that MU is given by this equation, where M squared is given by this equation, where this quantity Z naught is what we had obtained previously, which is this, right? So now if you take this and put it over here for Z naught, you get this very interesting expression. M squared log M squared equals minus 2 pi the Zeldovich number. So you get that expression. Okay. So now we're going to so I'm going to look at now we're going to plot. So here's a plot. Plotting M as a function. So I can plot M as a function of pi times the Zeldovich number. Okay. So this quantity. Okay. So if you plot that, here's this curve. So this is the so you get this following behavior as the heat. So here is plotted as a function of the heat loss parameter. As the heat loss is increased, the burning velocity decreases. Okay, so it follows this curve, right, and then it turns around. Okay, so this part of the curve is unstable, and that's the stable part. So therefore, you can find that there is a critical value of pi times the Zeldovich number, beyond which there's no solution. Okay, so that indicates basically the flame extinction, or the extinction of the premixed flame due to heat losses. Okay, so that's the extinction value, right? So again, we should give you an analysis to illustrate that the heat losses can extinguish a flame, right? Okay, now what is given here, which I will not have time to talk about, is that this curve, one can obtain this from rate ratio asymptotics. So this is rate ratio asymptotics, and that's activation energy asymptotics. And you can see that the extinction value obtained from the activation energy asymptotic is 0.61 at this point here, whereas from rate ratio asymptotics you get a 0.64. So the claim here is that they're very close. So therefore, activation energy asymptotics is a good approximation of the temperature sensitivity of hydrocarbon flames. And that's the point. So again, this is what I talked about today, and this is from rate ratio, which I will not have time to talk about. Nevertheless, we think that the activation rate ratio asymptotics must be more accurate because you lose a lot more chemistry. Okay, so therefore, so that's a good. Okay, so that's what I wanted to say yesterday. So hopefully, So now I'd like to move on to the third lecture. Right. Any questions on or maybe we can hold on to the questions to the end of the class, right? Yeah. Okay, all right, so now today I want to focus on activation energy asymptotic analysis of non-premixed flames. And the previous class was on premixed flames, so this is going to be on non-premixed flames. Right, okay. Now, again, this is very basic. In non-premixed combustion, the fuel and oxidizer are not mixed at a molecular level prior to, like premixed combustion, but the fuel and air are mixed at the molecular level. In non-premixed flames, they are not. All right, so mixing is a part of the which we need to analyze in addition to chemical reaction. Now, it turns out that in non-premixed combustion, a parameter that's a very important parameter appears, and that's the Dam-Kohler number. The Dam-Kohler number is defined as a ratio of a flow time to a chemical time, and this plays a central role in non-premixed flames. So it's like this is a characteristic diffusion time, flow time or diffusion time, and C is the characteristic chemical time. Now, now you can immediately notice that if the damp Coulomb number is small, that implies that the Tc is very much larger than Tf. This is it's a slow reaction, okay? Whereas the large damp Coulomb number, where the chemical time is much less than the flow time, this represents a fast reaction. The first thing I want to talk about today is the something called the Burke-Schumann flame. Okay, so here the point is that the theory of non-premixed flame was first developed by Burke-Schumann and Fendel in '65, and there's Lignan in '74 and Peters. So these are the things I want to talk about: the Burke-Schumann analysis and Fendel's and Lignan's analysis, as well as Peters' analysis. That's the okay. Right. The first thing there's of course the Burke-Schumann. We're going to look at the Burke-Schumann flame. Right. The Burke-Schumann performed analysis for large damp Coulomb number, what he considered was known as a co-flow diffusion flame, which I'm going to show it to you. Okay. Right. Yep. In Fendel, okay, following this analysis, Fendel performed asymptotic analysis, also non-premixed flames, for large and as well as small values of the damp Coulomb number. So essentially, Fendel's analysis was damp Coulomb number asymptotics. And as I said before, I mean, if for large damp Coulomb numbers, it'll turn out to be a singular perturbation analysis. And for small damp Coulomb number, it's a regular perturbation analysis. And it turns out that, if you recall, I indicated when I looked at the homogeneous reactor, the CSTR. Okay, in the CSTR, I illustrated to you that by using damp Coulomb numbers, you cannot predict ignition or extinction, right? So therefore, it turns out similarly because it's large. Since this was a large damp Coulomb number analysis, in the same way, Fendel cannot predict ignition or extinction. This was followed by Lignan and Peters, who performed the asymptotic analysis for large values of the activation energy. Okay, so this is activation energy asymptotics, and again, as I illustrated before, if to get ignition and extinction phenomena, you must have large activation energy. And then it was possible to predict critical conditions of ignition as well as extinction, right? Now, the rate ratio asymptotics are also performed in the asymptotic limits of large damp Coulomb number. Here, of course, we are able to predict, but again, all this work was on one-step asymptotics. So what I said right now only that you require large activation energy is required to predict ignition and extinction only is true for one-step chemical reactions. Whereas rate ratio asymptotics implies multiple-step chemistry. And if you have multiple-step chemistry, even for a large damp Coulomb number asymptotics, it's possible to predict ignition and extinction. Okay, right? Okay, all right. Okay, so now so again, the key point here is that in one-step asymptotics, large damp Coulomb number analysis one cannot predict ignition and extinction. You need large activation energy, and this is again similar to what was said yesterday. All right. Okay, here's a typical Burke-Schumann flame. That's the first thing I want to look at. You consider a co-flow flame, right? So this is a tube. So the fuel with the mass fraction of YF0 comes in from the central tube, and air comes from over here on this concentric tube on the outside. So the mass fraction of oxygen in air is Y0. So the subscript 0 applies to, so this is the mouth of the tube, okay? So the subscript 0 applies to conditions here at the exit of the tube. So the mass fraction of the fuel is YF0. There's a mass fraction of oxygen, right? So this is so-called over-ventilated flame. The over-ventilated flame implies that there is a large excess of oxygen. Okay, so as a consequence, the flame now looks like this. So because there's plenty of oxygen, right? I'm sorry, underventilated. Sorry, it's the opposite. Sorry, the underventilated flame. So it's the opposite. Sorry, this is a large excess of fuel. Because there's a large excess of fuel, the flame sits like that. Okay, and now you have this over-ventilated flame over here, which has a large excess of oxygen, which does that. Okay. That's the okay. that's the overventilated, that's the underventilated. All right, now the chemical reaction can be represented by one, we're going to represent chemical reaction by one-step process, nu of MF equals nu of 2M, okay? Those are the products. The radius of the inner tube is A, and the radius of the outer tube is B, okay? Now the radial coordinate is R, and the axial coordinate is Z, and Z is measured from the exit of the tube, right? Okay, yeah, okay, no, and the radial coordinate R is also measured from here, okay? All right, now these are the assumptions that goes in. Okay, there are several assumptions that go in the analysis. One of the assumptions is that the mass average velocity is parallel to the axis of the tube everywhere. So this says that the v velocity is parallel, and not only that, it is the same. Okay, so essentially we have a flow through a tube. One would expect a parabolic profile. Okay, but that's not. So we do not assume that. We assume here that it's just a plain parallel flow. Okay, it's not a parabolic profile. So this is perhaps one of the weakest assumptions. All right. And the total mass flux in the z direction is constant everywhere. That means rho v is a constant throughout the flame. That's again not a very good assumption, but we shall make that nevertheless. That's what Burke Schumann did, so we're going to use that. So the velocity is parallel everywhere. Rho v is a constant everywhere across. Okay, right? Okay, now the product rho d, the density times the diffusivity is a constant. This is a pretty good approximation. That's a good one. And we also assume that the axial diffusion, so that means the diffusion in the axial direction, which is along the tube, which is small in comparison to radial diffusion. So this is the diffusion. The diffusion in this direction is small in comparison to diffusion in this direction. This is again a very good approximation. Okay, it's like the classical boundary layer theory. So therefore, that's okay. So these are, and then the reaction, there exists all the chemical reaction takes place in the thin flame sheet. All right. So this is a flame sheet. So these are very good approximations, but these two are not, or the first two. Okay. So that's what the analysis is for. All right. Following what Professor Williams did in his first lecture, you define it. So you have this quantity alpha, which is a mass fraction of the fuel. This quantity alpha alpha O2, which is a mass fraction of oxygen, right? Molecular weight of oxygen, that's the stoichiometric coefficients. So this is how alpha 0, alpha F, and alpha O2 are defined. And you saw in the first lecture, you can define a coupling function beta, which is alpha O2 minus alpha F, and this coupling function should satisfy this particular source-free equation. And this is because the reaction is one step, so the rates at which the fuel is consumed, okay, and the rate at which the oxygen is consumed are about the same because there's only one reaction, okay. So when you combine them in this particular form, the source term in the fuel and this will source from the oxide disappear. So this is the equation for the coupling function beta in terms of the radial coordinate. Okay, that's what it is. Okay. All right. Now, so that's the equation we want to. So we're going to solve for beta. We're going to solve this particular equation. All right. Now let's look at the boundary conditions. The boundaries. Remember that beta is this. Okay. So in the inner. So let me. Okay, now we have, so this was the Burke-Schumann flame, okay? So this was YF0 over here, and this is YO2, O0, so this is where the oxygen is, this is where the fuel is. You can see that if you look at these boundary conditions, you can see that in the region, and A was this is A, oops. A is, I forgot which was diameter. Okay, that's A. Oh, I'm sorry, A was the radius, not the diameter, right? So the A is the radius, okay? And the radius, okay. Oh, yeah, okay. Yeah. Right. So, okay, so you can see that in this, in the inner tube here, okay, no oxygen is present. So therefore, beta, which is the coupling function, therefore, if you look at beta, must be equal to just simply alpha, simply should be equal to alpha f, okay? So, yeah, okay, alpha is defined with negative sign, okay? So therefore, so this is what beta is, right? In this, okay, and the value of beta on the outside, on the outer tube here, in the region R greater than A but less than B, in this is this, okay, because there's no fuel present. And now at the now at R equals B, that is at this boundary over here, right? The point is that there's no net flux of the reactants flowing out of the tube. Okay, there's no net flux. And then since there's no net flux, that implies that the gradient d beta dr must be 0. Okay, and this is applied at that wall over there. Okay, on the outer tube. So there's no net flow of any mass across this boundary, and that means that the gradient of beta at R equals B should be equal to 0. Okay, so that's the equation, right? And those are the boundary conditions that we need to apply to solve the set of equation, all right? Okay. All right. And now I'm going to define a few more, for convenience, we're going to define a few more, we're going to introduce a non-dimensional coordinate, C, which is R divided by B, define so this is a non-dimensional radial coordinate, a non-dimensional axial coordinate, defined in this fashion, okay? So all these, all these quantities are known. Okay, d, v, b squared, these are all known, right? So these are the two non-dimensional variables. We define a reduced parameter c, which is the ratio of the a over b, and this is the stoichiometric coefficient nu. So again, nu, c, and all these things are known, right? And this is and you define a reduced dependent variable in this. So gamma, which is again related to b, in this beta in this form. All right. It turns out if you introduce all these non-dimensional variables into this equation, right? It turns out that you get, so this is you get this following expression for gamma. Okay. So now the boundary conditions for gamma are again the same as before. It's just pretty much the same problem, okay, except written in terms of non-dimensional variables, non-dimensional and normalized variables. So that's the equation, right? Those are the boundary conditions, okay? Now it's possible, it turns out that it's possible to integrate, get a closed form solution to this, right? And this is what I urge you to do. Since these notes, since these view graphs are on the web, I suggest that you take this equation, apply these boundary conditions, and try to get this, so that get that solution. Okay, it's possible to do that. Okay, you integrate those equations, and you should do that. Okay? So that's the solution. That's gamma. So again, it's integration of that equation. Okay, that's the expression for gamma. So that tells you. Okay, that's it. All right. Where J0 and J1 are Bessel functions, right? And the J1, so these are the phi n are the roots of the Bessel functions, right? The J1 0 equals, and phi n, these are the roots of the Bessel functions, all right? Okay, so now the aim of this work is to predict the flame shape and the flame heights, all right? That's the ultimate aim, right? Now it's, since, if you go back to this here, you can see that now at the beta is this coupling function alpha 0 and alpha f, right? Now at the flame sheet, both the fuel concentration of the fuel as well as the concentration of oxygen is 0 at the flame sheet. Okay, because in the large Dam Coulomb number limit. So therefore, the contour of the flame is given by setting this beta equal to 0, right? So if you do that, if you take this expression and you put gamma, which is again beta, if you put gamma equal to 0, you get a relationship between psi and eta, okay, and that is the flame shape. All right, so that's the flame shape is obtained simply by putting this equal to 0, so you get the flame shape that way, right, between those two variables. All right. Okay. Now so here is a plot of so this is the over ventilated flame, okay, that's the under ventilated flame, okay, obtained from is precisely what I told you. So if you want to plot the contours, you really don't need to take all these terms into this equation, because you see there's this exponential term that appears, okay, and this phi n increases. So it is actually sufficient to take perhaps one term, or at the most maybe two terms in the exponential. I can neglect the rest. Okay. So therefore, in this expansion, it's sufficient just to go from n equals 1 to perhaps 2 or something like that. Okay. Or even the first term is sufficient. Right. So by doing that, you can now get the flame shape, which is obtained from that. Okay. That's the flame shape. And now you can also get the flame. So here's an expression of the flame height. To get the flame height, you can see that if it's an over-ventilated flame, then if you set eta equals 1, I'm saying C equals 1, then you get then you get when you set C equals 1, then you can get the flame height, okay? Or if you set C equals 0, you can get the flame height for the that's the over-ventilated flame, that's the under-ventilated flame, okay? So what you see here is what is written here is the flame height for an under-ventilated flame. So which is this one right here, under-ventilated flame, and which has been obtained by setting C equals 1. Okay, so therefore, right. So that's the answer. Okay, so what we have learned here is that using this very simple method, you're able to get the flame shape, okay, as well as the flame height, right? And it turns out that this is remarkably accurate, these expressions, okay? Even though we have made two drastic assumptions, that the velocity is constant everywhere, as well as the fact that the mass flux is constant. Okay, in spite of that, and also buoyancy has been neglected in addition. Okay, so in spite of all those approximations, still the flame height and the flame shape that you predict from this analysis are fairly accurate. Okay. Okay, so that's the first thing I want to look at. The second problem I want to look at is is analysis by Lignon. This is a counterflow non-premixed flames for large value laser activation energy. So this is a very classic analysis of a diffusion flame structure. So and we will use a large activation energy and illustrate that with large activation energy you can predict ignition as well as extinction of this flame. Okay, right? Okay. Now here, so this is again I urge you all to read this paper by Lignon, okay, which is an Astronautica, and this is actually a must reading. This paper, okay, it has a lot of good information on diffusion flame structure, right? Okay. So here's the analysis of you consider two jets flowing towards a stagnation point. So you have a flow coming from plus infinity. It's an oxidizer. So this contains oxygen. It flows towards a stagnation point. And on this side, you have another stream that contains fuel that flow towards. So these two jets flow towards each other. Okay? And there is a stagnation plane that's formed here. All right? And it turns out that depending on the concentration of the fuel in the oxidizer, or rather the concentration, how much oxygen there is in the oxidizer, or how much fuel there is in the fuel, depending on this, the flame will either sit on this side, on the oxidizer side of the stagnation plane, or on the fuel side of the stagnation plane. It's also possible to stabilize it right at the stagnation plane. Okay, so that depends on the concentration of fuel or the concentration of oxygen in the oxidizer, right? Okay, now for simplicity in the analysis of Lignon, he assumed that the velocities that flow towards the stagnation plane with equal velocities. Okay, so it's equal velocities, and the Lewis number is 1. That means, we saw what the Lewis number was. It is a ratio of the mass diffusivity to heat diffusivity. Okay, and that's assumed to be 1. All right, so heat and mass diffuse at the same rate. And now we have assumed that the chemistry takes place by a one-step process, fuel plus oxygen going to products, and it will be assumed that the activation energy of this particular reaction is large, right? Okay. And again, the reaction is first order with respect to the fuel and first order with respect to the oxygen. We also saw that last time. Okay, we always assume that the reactions rates were first order with respect to the fuel and oxygen. Okay, right. Okay, okay. Now I want to illustrate that it has been shown by Fendel that in this particular configuration, in this counterflow configuration, he has shown that along very close to the axis of symmetry, all right, the mass fractions or the scalar quantities like the temperature and mass fraction of various species are only functions of the axial coordinate. Okay, they do not depend on the radial coordinate. So that was an analysis which was in Fendel's paper. Okay, whereas of course the flow field is two-dimensional, but the scalar field is one-dimensional, right? So we'll make that assumption, all right? So we'll and then of course the normal component of the normal, as I said, the flow, the reactants come from minus infinity and the flow towards each other, okay? And the and you introduce this quantity, the strain rate. So the axial component of the flow velocity v can be written as a strain rate a times z. Okay. Well, this z, I put a little hat on top to show that this is a dimensional axial coordinate. Okay. So the velocity, so the flow comes in. So the flow comes in like this, v. So that's actually a times z. So that's the way it's flowing. And of course, so z is the axial coordinate with z being equal to 0 at the stagnation plane. All right. So if we're at the stagnation plane, the normal component of the flow velocity is a 0. All right. Okay. Okay. So okay. Now this is a non-dimensional. So now we want to non-dimensionalize the independent as well as the dimensional variables. The normal coordinate z is the non-dimensionalized with division by this, where di is the coefficient of diffusion, and a is the strain rate. So if you divide the z hat divided by that quantity, that gives you, that is z, the non-dimensional z. Okay. The temperature is non-dimensionalized with respect to this T. Okay. So where YF infinity is the mass fraction of fuel at minus infinity, Q is the heat release, and C, this is the heat capacity. So the temperature is non-dimensionalized with this. All right. And the and then also we define a few of these normalized variables. You define a YF, which is YF divided by YF of minus infinity. YO is YO2 over that, okay? And there's a parameter mu. And this is a very important number with the Damkohler numbers that appears. The Damkohler number here, so that's the strain rate in this equation is actually is the reciprocal of the characteristic resonance time, because the strain rate has units of 1 over seconds, right? 1 over time. So therefore the reciprocal of that is the characteristic flow time. So you can see that the Damkohler number has a in the denominator. So therefore that's the the characteristic flow time appears here in the numerator, and this is the reaction rate. B is being the frequency factor, okay? And that has units of 1 over seconds, which represents the characteristic chemical time. So here you have the characteristic flow time, and B has the unit, that's the characteristic chemical time. Therefore, that's the Damkohler number that appears in the analysis, right? Okay. So now, so with these non-dimensionalized variables, non-dimensionalized Z, normalized mass fractions, and the D given in this form, it can be shown that the energy conservation equation can be written in this form. Again, I strongly urge you to write down the energy conservation equation, okay, and convince yourself that that is the energy equation in the non-dimensional form, okay? Now, everything here is non-dimensionalized. The temperature is non-dimensionalized, and so this TA is the activation temperature, which is also has been non-dimensionalized by division with let's see, where do I have that? Okay. Okay, here. Here, that's also non-dimensionalized by division by this quantity. So everything is non-dimensional in this equation. Okay. Sorry. Okay. Now you can write a similar equation for the fuel as well. The same equation for the fuel, except that a positive sign will appear with this rate. Okay. So say one can write the same equation for the fuel with a positive sign here, and the same equation for oxygen again with a positive sign here. Therefore, one can immediately write these coupling functions. Because so you can get the coupling functions, between coupling between temperature and the fuel, the coupling function between the temperature and the mass fraction of oxygen. You can write these two equations. So essentially, what it is that you have this energy conservation equation and these two coupling relationships. Okay. Now it turns out that one can actually integrate these. Okay. Okay. All right. So again, these are the boundary conditions at t equals. So these are the boundary conditions that apply t equals t infinity, y equals 0. So this is at plus infinity. Okay. Plus infinity, and these are the boundary conditions at minus infinity. So these are the governing equations, and those are the boundary conditions. All right. Now, for simplicity, I will assume that the temperatures at the boundaries, the temperature of the fuel, are the same for simplicity. All right. So you assume that T infinity and T minus infinity are the same on either sides. Okay. All right. Okay. So now this is now it turns out it's convenient to define a quantity x. So this is simply so this is an important step here. What's done here is that you define a quantity x, okay, which is simply satisfy that particular equation, right? So let's look at this here, all right? And this is somewhat similar to this, except that there's a so this is x, okay? That's the definition of x. Now I'm going to say that x is the solution to that equation, such that z equals minus infinity, x equals 1, and z equals 0, at z equals plus infinity, x equals 0. Okay, so I want to solve that equation subject to these two boundary conditions. And this is a problem we looked at yesterday. Also, it's a classical, transient heat conduction type problems. And then you see the solution to this. So you can show that x depends on z in this particular fashion. So here, what I've done is simply define an x. Okay. That satisfies this set of equations, and you find the solution to that equation of z. Now, what is interesting about this is that if you take these set of equations, all right, and instead of z being the independent variable, if you write these equations in terms of x as the independent variable, okay, right, then it turns out that these equations take a very simple form like that, okay. And again, this is a very simple, it's very easy to show this, right? Okay, and you can show that, so basically what you need to do is that you take these conservation equations, okay, rewrite this conservation equation in terms of with x as the independent variable. What's nice here is that these are the equations that result. So what's nice about this set of equations is that the first derivative has disappeared. Okay, the convective terms have disappeared. It doesn't mean we have neglected the convective terms. In this particular transform coordinate x, that simply drops out. But actually, the convective terms appears here. Okay, that's where it appears. So now this gives a appearance of a very simple diffusion reaction balance type of an equation. Okay, it's much easier to analyze these equations than to look at that. Okay, right. And we shall see later on that this quantity x is actually something called the mixture fraction. I will show that later. Okay. So that's the energy equation. These are the species balance equation. Okay. Now the boundary conditions are t equals t infinity. The same set of. Okay. Now x equals 0. As you can see here, x equals 0 z equals infinity is actually x equals 0. So in this actually the things have actually flipped. I mean, if you look at here, the oxidizer was here, right? You can see that the oxidizer here, this is z infinity, and this is z minus infinity. In terms of x, this is actually x equals 0, and this is x equals 1. All right? So that's how it has turned around, right? Okay, so that's so now those are the boundary conditions. T equals t, y equals 0. You get those boundary conditions. And now it turns out that you can solve these, you can integrate these two equations, right? So if you integrate them, you get these coupling relationships. So this couples the oxygen to the temperature, and this is the fuel to the temperature. They're coupled in this fashion, okay? So basically now I can take, in principle, I can take this YO in terms of temperature and substitute it here, and YF in terms of temperature and substitute that over there. So now you get only one equation in temperature, okay, which is expected to satisfy these two boundary conditions. T equals T infinity, x equals 0. T equals T infinity, x equals 1. Okay, so the entire diffusion frame problem has been reduced to solving one equation here, subject to these two boundary conditions, right? Okay. By the way, you have any questions on this so far? Beg your pardon? X is the independent variable, yes. Which one? Yeah. This is good question. Okay, this d squared in principle can be written in terms of x. Okay, right? Okay. So there's this relationship. In principle, you can do that, right? Okay. Just convenient to write it that way. Right. Okay. Any other questions or yeah? Yeah.
Previous slide, previous one where the fuel oxidizing picture is here.
Yeah.
So at stagnation plane, what happens exactly to the plane?
There's nothing. I mean, it's just this is so really what the point. That's a stagnation flame. The flame is sitting over there. Okay. So essentially, what's happening here is in this particular scenario, the fuel is convected here. Okay, and from here on, fuel gets into the flame by diffusion. Okay, so the oxidizer enters in, of course, by convection and diffusion. All right, that's it. So the reason is that if you have a large excess of fuel, let's say mass fraction of fuel is unity, the diffusion flame always seeks a position of stoichiometry. Okay, so the flame is such that the diffusional fluxes of fuel and the diffusion flux of oxygen from either side must be in stoichiometric proportions. Okay, now let's say the flux over here is much larger. If you take the flux of the fuel coming from here, let's say it's very much large. Okay, then what happens is the flame is going to sit over there, right? So then, so now it gets enough oxygen, and therefore the fuel has to diffuse through this. Okay, okay. So that's why it's. And for example, if you have large excess of air, okay, or also a large excess of oxygen, pure oxygen, for example, okay, then the flame is going to sit on this side, okay, because it doesn't have enough fuel, so it's going to sit over here. So now the oxygen has to make this extra effort to go across the stagnation plane. Right. Yeah.
So, going by that,
What's that?
if you have a large oxidizer, then how is the velocity matched? Because we assume that ρB is constant.
Yeah, I mean, the concentration, mass fractions. I'm talking about the mass fractions, not that the mass fraction of oxygen here is y0 infinity, right? I make y0 infinity 1. That's what I meant. Correct.
We also assume that the densities are the same and the velocities are also the same.
Yes.
So, how do we achieve underventilated and overventilated conditions?
It turns out that, yes, we have said that the velocities are the same and the densities are the same, but that's only for convenience. That can easily be relaxed. Okay. That's not it. It turns out that if you make suitable transformations, you can make it look as equal. So that's not a real restriction. Just to make it, the point is to make the analysis simple. But we will apply to situations where the densities are different. Yeah, I mean that's a thing that comes from the previous Burke Schumann. I mean you can think about a over-ventilated flame as being large, or YO infinity is 1, for example. Okay, so the over-ventilated flame could be over there, all right? An under-ventilated flame, perhaps you can call this an under-ventilated, and that you could call that over-ventilated. Big one?
At the incline of the tube,
Yeah.
we have
There's no tube here, these are open.
in the case of the tube, the previous case,
Yeah.
not co-flowing, non-premixed.
Mhm.
This is the case of.
This one?
In this case, sir. So we have at the incline of the tube, we are having certain velocities of fuel as well as the oxidizer.
Yeah, yeah.
So and the mass fractions will be accordingly to the in the part of oxidizer, the mass fraction of the oxidizer will be there only. So and how can we get to know that which type of flame will be formed in that case?
It depends on the basically it depends on the mass fractions of oxygen and the mass fraction of fuel here. So this is it just depends on these things basically on how much. For example, if you have the mass fraction, this is let's say 1, okay, and you have this, and then let's say this oxygen is pretty small, right? Then in that case, that would be that it will form that, right?
But in the central part, the mass fraction of flame will be 1, and then in the angular part, the mass fraction of oxidizer will be 1.
Where? Oh, you meant here?
Yes, sir.
You are looking at a pure fuel, yes. But then depends on it depends on the new Fs and the new O2s, correct? Right, that appears in front as well. Yeah.
So in what application this underventilated forms are developed? Application of this underventilated fluids.
I mean, I'm not really looking at applications here, just to show that you can get these two things, the two different types of a configuration, right? So particularly, I mean, there may be reasons you want this, or may be reasons you want that, right? Okay.
So,
Yeah.
how do you obtain the strain rates?
Well, the strain rate. I think I don't want to go into that question a whole lot, but strain rate is simply, the definition of a strain rate is a solution to the Euler's equation in the outer flow, correct? If you integrate the Euler's equation, okay, and then if you integrate the Euler's equation, you get a velocity profile, okay, and you take the gradient of the velocity profile and evaluate that at the stagnation plane, right? That's the strain rate, okay. So right now, as far as this right now, what is concerned is that we're simply going to say that you have a flame. This is I'm going to presume to be given right now. The strain rate is a given, right? Okay, the flow is we simply assume that's given, okay, rather than the velocity. The strain rate is prescribed. It's very similar to the classical. If you read Schlichting's book, he has a flow towards a stagnation plane, correct? I don't know if you're aware of that textbook, right? And there they simply state that the velocity is u equals a times x, or v equals minus a times y. And that's the solution to the Euler's equation, right? The mass conservation equation, right? Okay, I think I'm going to cut my last question. Okay, yeah.
In mixture fraction approach, the main assumption is equal diffusivity.
Yeah.
Is there any assumption like for even analysis?
In an assumption for what?
Mixture fraction approach.
Yeah.
When you use to combine equations, you assume that the diffusivity is equal. So that's why we use to combine equations.
Mm-hmm.
Is there any assumption like this in the analysis?
Right, okay, in this particular analysis, we have assumed equal diffusivities, right? We have said Lewis number equals 1, correct? That's what I've done here already, okay? But I'm going to say that, no, that's not a restriction. I mean, you don't have to have equal diffusivities. You can simply define an X in that form, okay? And then include the effects of diffusion as non-unit Lewis numbers as well, right? Okay, I can still define an X. Okay, this is completely independent of whether you have Lewis number 1 or not non-unity Lewis numbers, right? And so one can still analyze it. So my point is, here I'm assuming Lewis number 1, okay, but that we need not be restricted to that, okay. Okay, I think I'm going to continue on, so otherwise it's okay, no. All right. Okay, so now that we have, so now the point here is that this is the equation, right? And from the coupling relationship, we obtain a mass fraction of oxygen, and that's the mass fraction of fuel, okay? And you can see the oxygen is related to temperature, and the fuel is related to temperature as well, okay? All right. Now we proceed with the analysis. It turns out that you can identify in this flow, okay? you can, it turns out that, this is then, oh, you know what happened here? Oh, okay. It's coming back, right? Oh, okay. All right. Okay. Now, in this counterflow problem, you have this. Of course, you have the stagnation plane. Okay, there you go. You have the stagnation plane, and then you have the flow coming towards the stagnation plane. Okay. Sorry. Okay, it's not it. Sorry. So it's your flow coming. Now you can identify, I should see, you can identify, you can say that sometimes let's say that's where the flame is, okay? Now you can talk about situations where the flow field outside the flame, being here and here, you can talk about, you can say that, you can classify them into two types, okay? Either the flow field is frozen or the flow is in equilibrium, okay? So the idea is that the flow can be frozen. So I'm going to look at different combinations of. So it's essentially. So you can have. So here is a. Okay, sorry. All right, there you go. So you can now. Let's say for example, one part of this flow is frozen. What does a frozen flow mean? A frozen flow means that the right-hand side here, okay, is zero. Okay, there's no chemical reaction taking place. Okay, so for the frozen flow, this is the temperature profile is given by that expression in the regions where the flow is frozen. Okay, now in the regions where the chemical reaction is in equilibrium, right? What the equilibrium flow simply implies that if you look at this particular equation, for example, that if you have a large Damn-Coulomb number, then this is very large. So for that to be finite, let's say if you have a large Damn-Coulomb number, then the product YF, Y0, this particular product must be 0. Okay? So for the equilibrium flow, it requires that YF, YO is 0, and for frozen flow, it requires that D squared T dx squared is 0. Okay, so these are the two cases, right? Okay, so let's say that, so if in that region, if the flow field is frozen, or then this equation applies. Okay. Now, for some reason, that region is in equilibrium. If you have equilibrium, I said equilibrium flow implies that YF, Y0 is so YF, YO is 0. So that means either YF is 0, okay, or YO is 0. Okay. So one of these things must be true. Okay. So then if you apply, if you go back to the coupling relationships, if you get, so in the regions where YO is 0, then the temperature should be given by temperature T is this, okay? In the regions where YF is 0, the T is given by that expression, okay, right? So where do you think that would happen? I mean, it would happen, for example, since in this particular configuration in terms of X, so this is X equals 1 for here, X equals 0. In this particular configuration, there's a flame over here, right? So this could be, for example, a region where if this is in equilibrium, that means YO could be 0 here, right? And in this side, since if this is in equilibrium, YF can be 0 because there's no fuel on the other side. Okay, so those are the two limits that you can have. So the temperature profile in the regions where equilibrium flow regions where YO is 0, the temperature profile is given by this, and for YF is 0, the temperature profile is given by that expression. Okay, so therefore that's how I've written here. So in the regions where YO is 0, that's the temperature profile. In the regions where YF is 0, that's the temperature profile. Now it turns out in analysis of Lignan, he looked at different combinations. I mean, for example, you have frozen flow on both sides. You can have so you can have equilibrium flow on both sides. You can have frozen flow on this side and equilibrium flow on the other, or you can have equilibrium flow on that side and frozen flow on the other. Therefore, you got 4 different flame structures are possible, okay, for the flame. And then turns out that, this is what it, this is this is the so-called the frozen flow regime. So let's assume that you have a case where both sides are frozen, okay? So then, and then both sides are frozen, so to the leading water, this must be true. Okay, the second derivative is 0 here as well as over there. So that's the leading order, this is true. Okay? And then in that case, since I've assumed that the temperature profile, okay, is T infinity on either sides, right? So since I assume T, okay, so the temperature to the leading water, the temperature profile is T infinity everywhere, and there's no YO and YF are given by these expressions. Okay, so if you go back to these coupling relationships, you can see that if T equals T infinity, YO is given by this, and T equals T infinity, YF is given by that. Okay, so the frozen flow regime, that's the equation, and that's the to the leading water. Now it turns out that if one does a regular perturbation analysis of this regime, you can predict critical conditions of ignition. Right. So I'm not going to do that here, but so this is, if you want to predict ignition, one has to analyze this particular regime. Okay, the frozen flow regime. There's another regime. So this particular regime is important for analyzing auto ignition. Okay, right? Now, in the auto ignition, as you know, that reaction zones are frozen everywhere, and suddenly it ignites. Okay. Now, there's another regime called the partial burning regime. In the partial burning regime, there's frozen flow on either sides. Okay, and there's a thin reaction. There is a thin reaction zone. Okay, again, it's frozen flow on either sides. Now, in this particular case, it turns out that fuel, because this is a weak flame, the fuel that comes in from that can leak through the reaction zone. And again, since this is a weak flame, oxygen can leak. So you have both leakages of both oxygen and fuel from the reaction zone. Okay, because it's a weak flame. Not because there's leakage, not because there's excess oxygen or excess fuel, because the flame is always stoichiometric. It's just that the reaction rates are weak, and that allows to mix leakages. Right. Now it turns out that this particular until recently it was this regime was considered to be not useful because but more recently we find that for example, if you want to predict cool flames exist in this partial burning regime, right? Okay, so that's so this is used in analyzing critical condition of auto ignition. This particular regime is useful for analyzing cool flames. All right. Okay. And then now we have another thing called the premixed flame regime. In the premixed flame regime, this is the fuel side, which is over here. There's equilibrium flow on this side, and there's a frozen flow on the. Now it turns out for this value of alpha, one can show that alpha has to be less than 1 for this particular case, for this particular scenario to happen. All right. When alpha is less than 1, and then one can have equilibrium flow on that side, okay, and frozen flow on this. So since there's equilibrium flow on this side, this is the fuel side, so therefore YO must be 0, okay. So you can see that. So in the region where the flame sits in a position called XP, okay. So in the region X greater than XP, which is here, the YO is 0, so that's the temperature profile, right? And in this region, okay, the temperature profile is given by. So if you assume that the temperature at the flame is Tp, you can integrate that equation, and you can get the temperature profile in this region, again, which is here, okay. So you get the temperature profile in this for the frozen flow as well as the equilibrium flow regime, all right? And also turns out you can get, since this particular case, there's leakage of fuel, right? And the leakage of fuel is given by that expression. The reason why this is frozen is because fuel can leak. And since there is oxygen on this side and oxygen and fuel are not reacting, even though there is fuel present, that's why the flow is frozen, okay? All right. Okay, and then the other thing you can have is so-called for alpha greater than 1, it's possible to have frozen flow on this side and equilibrium flow on this side. In this case, you have leakage of oxygen rather than leakage of fuel. Okay, again, you can get the temperature profiles, okay, and also the leakage, the leading water, right? And this is the one which is of most interest. And this is the Burke-Schumann flame, for example. This is the Burke-Schumann flame, which has equilibrium flow on both sides. Okay, so maybe I should look at this in particular detail. Now, in this, so that's the flame. Okay, just like in Burke-Schumann analysis, in the flame sheet approximation, we were able to get the flame shape and the flame height. Okay, in this equilibrium flow approximation, we can get the flame. We can get without looking at chemistry at all. Okay, we can obtain the flame temperature as well as the flame location. Right. Now, let's see how to do that. You see the here. Maybe I can just go to another page. If you look at the if you look at the coupling functions, okay, let's see. Here it is. Yeah, you can see that y0 is given by alpha times alpha 1 minus x, okay, plus t infinity minus t, and you can see that yf is given by x plus t infinity minus t. Okay, so it's, if you have in the regions where yo equals 0, okay, then you can see that the temperature T is alpha 1 minus x plus T infinity. In the regions where YF equals 0, right, the temperature T equals x plus x plus T infinity, right? Okay. So now if you equate them, I sorry, I went too fast, okay. Okay. Okay, so now this is what I've written here. So I've written that in the region where YF is 0, that's the temperature profile, and that happens, here, so that's the temperature profile in this region, right? In this region, YF is 0, that's the temperature profile, and this region, with the region x greater than xc, that's the temperature profile. Okay, so now I can equate these two because at the flame, this must be equal. Okay, this should be equal to that, correct? So if you equate T infinity, at the flame, this is true. T infinity plus x must be equal to T infinity times that. Okay, so now therefore, now I can calculate the flame. So if you equate these two, you can get the flame position xe in terms of alpha, which is this, okay? Now we take this alpha and substitute over there, they can get the flame temperature. So you can get the flame temperature and the flame position in this diffusion flame regime, right? Now I want to quickly show that in Lignan's analysis, this is a regular perturbation analysis. So Lignan looked at the frozen flow regime, which is he calculated critical conditions of autoignition. He looked at that and did a regular perturbation analysis, and he was able to obtain the lower part of the S-shaped curve. He obtained that result. And from here, he was able to predict the Damn-Coulomb number at ignition. So that's the Damn-Coulomb number at ignition. Okay? So you can see that the, he predicted that, so those are the temperature profiles. Okay? You can see that, you can see that, that's the top part of the curve. That's this, so this is the top part over here. And then somewhere in between here, you can see that if you look at these numbers, okay, the Damn-Coulomb number is increasing, and there's a decrease. Okay, so that means this probably corresponds to something like this. Okay, two solutions here, and there's a solution in between. There's one critical value delta 0 in between, where that represents the critical conditions of autoignition. Okay, so you're able to predict the critical conditions of autoignition from this analysis. Right? Okay, now this is from the equilibrium flame structure. He predicted the critical conditions of extinction, and then he also predicted Damn-Coulomb number at extinction. So this is the analysis I want to go into a little bit of detail. Okay, right. So the diffusion flame regime. Okay, right. Okay. This is to summarize, that's the ignition problem, which I will not be talking about. But this is the extinction, which I'm going to talk about. So to do the extinction, I'm going to switch to the analysis by Peters. That's the Peters analysis because it's a little bit more general. and it's in terms of mixture fraction, right? Now, in the flame rate formulation of Peters, again he assumes that the Lewis number is 1, all right, and D is that, okay. He writes a quantity mixture fraction Z is defined by this equation, and this is somewhat similar to the quantity X that we looked at before. So this mixture fraction, that's the mixture fraction equations, and this is the X that we had before, okay, and this is the energy conservation equation, right? It has a radiator term as well as a transient pressure term, because it's a transient equation, all right? And that's the mass equation for the mass fraction. So these are exactly like what we had before, except that we didn't have the transient terms, right? And so basically this is X. Z is actually X, and that's the mixture fraction, okay? Right. Oh, here, no, that's written again. That's the equation for the mixture fraction, right? And it doesn't contain the source form. Again, it doesn't contain the source term, right? Now, let's see what, okay. Now, of course, this mixture fraction, Z, is a function of the spatial coordinate and time. Okay, so those are the two quantities that appear. All right. Again, all these slides are from Peters, from Aachen, all right? Okay. Now let's look at typical diffusion flame. You know, as I said, the advantage of using the mixture fraction or the coordinate rather than the spatial variables, because it becomes somewhat coordinate independent. It applies to all flames. Okay, all right. So here is a diffusion flame. There's a fuel coming in from here, air coming from the side. You can see that in the mixture fraction space, Z equals, just like before, X equals 1 was the fuels. Here is Z equals 1. Z equals 0 is the oxidizer, okay, and the flame sits something like this, okay? And the X1, X2, and X3 are the spatial coordinates, and Z, of course, is the mixture fraction. Now, what is done here is that you, if you look at one particular, let's look at a flamelet, a thin flamelet, okay? You define a coordinate Z, okay, that is normal to the flame, okay, right? Okay, and the other coordinates, so this is basically the coordinate system. This X1 is now Z, okay? Then you define another X2 and an X3. Okay, so the key point is that the Z, the coordinate Z is defined normal to the flame. Okay, all right. The coordinate Z. Okay, so that if you make a transfer, now if you take this set of equations, all right, and transform this from X, transform to a new set of coordinates, where you replace the coordinates where Z X2 X3. So you have this Z X2 X3 in time. This is the coordinate transformation here. But Z2 is actually equal to X2, Z3 is X3, and T equals tau. So you make this coordinate transformation. All right. You make the coordinate transformation. So these are some details of how the coordinate transformation could be made. All right. If you make the coordinate transformation, this is the equation that comes in, results. Right. So for temperature, based on this coordinate transformation. All right. Now, the interesting thing about this is, I can see that interesting things about this is you make the following statement, that we state that the gradients of temperature in the Z direction, okay, normal to the flame, are more dominant in comparison to the gradients in the X2 and the X3 direction. Okay, you make that, which is fairly reasonable. Okay, if you make that approximation, if you look at this particular equation, this becomes the dominant term. Okay, all the other terms have derivatives with respect to Z2 and Z3, but Z2 being X2, Z3 being X3. So all these terms become unimportant. Okay, right? So the resulting equation is just this. Okay, right. Okay. So again, this says that this is the dominant term. Okay. So now the energy conservation equation can be written in a very simple form. This is actually very similar to what we had before in the Nyan's analysis, except that here you have a new, except that now you have the new term that appears here, which is called the scalar dissipation rate. okay, which is okay, yeah, okay, let's see. Yeah. Okay, so this is okay. So again, let me continue on. This is the equation that results. Okay, so yeah, let me go here. Okay, right. So now you define a quantity called the scalar dissipation rate, which is this. Okay. So now this equation, the equation which I had here, okay, this particular equation can be written in terms of the scalar dissipation rate. Can be written in this particular form. All right. So that's the so-called flame rate equations. So the temperature time written in terms of this quantity Z, which is the mixture fraction. Okay. Right. So and an important term is the scalar dissipation rate that appears. Okay, which is the inverse of the characteristic diffusion time. All right. Okay. Now, if you recall that yesterday we looked at the classical homogeneous reactor. Okay. For the homogeneous reactor, it turns out that if you put the scalar dissipation rate equal to 0, the equation for the homogeneous reactor are recovered. Okay, with the ones which I did yesterday, right? Okay. Okay, and now I'm going to, so that's a scalar dissipation at the temperature. So now we're going to use this equation to analyze a planar counterflow, a simple counterflow diffusion flame. Okay, yeah. Okay, okay, all right. So this is that's the equation you want to look at. Okay, the classical. So that's the temperature, the heat release term. Okay, that's the scalar dissipation rate that appears. Again, this is very similar to the equation that we had before, right? Now it turns out that if you analyze this equation, you can obtain this classical C-shaped curve, and then of course this is the stable branch of the C-shaped curve. That's the unstable branch, and you can get the quenching condition. Okay. All right. So so now, okay, now to analyze this equation, you have the so again that's the flow. Okay. And you can have so that's the energy conservation equation, right? And you can get a similar equation for the fuel. For example, the equation for the fuel will look something like rho chi st over 2 d squared yf dz squared equals that be wf omega. Okay, that's with a positive sign because fuel is consumed, and you get a similar equation for oxygen, 2 dyf dz, or there must be a stoichiometric coefficient that appears in uf. And for oxygen, you have nu O2, WO2 times omega. You get a similar equation for oxygen, and you can again obtain coupling functions between them. You can get coupling functions which will look like partial z squared, right? So I can write t times Cp over capital Q, right, plus YF over mu F WF equals 0. Okay, so that would be a coupling function for oxygen for fuel, and you can get a similar coupling function for the temperature as well. Okay, similar coupling function between the temperature and oxygen. All right. Now with those coupling functions, it's possible to construct the so-called outer structure. So this is the classical Burke-Schumann structure. Okay, you can obtain by solving again by assuming there's an equilibrium flow on either side. So the equilibrium flow on either side, so one can now construct. So this is the outer structure. You can get the temperature profile. This is the outer temperature profile, and the flame sits at ZST, and ZST is the same like the flame position that we had before. So that's the flame temperature TST. And this is you can see that the fuel comes in here, and the constant, it flows this way, okay? Goes to 0 at ZST. That's the profile for oxygen, okay? So they all disappear. So this is the classical outer structure for the diffusion flame, right? Anyway, do you have any questions on this so far, or does anyone have a question? Yeah.
So for the Boltzmann solution, the second derivative is taken to be 0, and we get the same solution even for infinitely fast chemistry. So
Which one?
this one.
Yeah.
So in that case, it's not exactly that the source term is 0 throughout, right? That is like a Green's function. At the plane location, there is a temperature derivative. So this seems to be an inconsistency. Like you're artificially imposing the boundary condition here, assuming second derivative is 0, and then neglecting the source term at the plane location.
No. This is no. That's not the point. The flame is located over here. It's a very thin sheet. Okay. So the idea is when I say that the is equilibrium flow, you simply say that we will be analyzing. I'm not saying we will be analyzing the structure of the reaction zone. Yes. Okay. So this is so all I've done is look at these coupling functions. Okay. Again, it's a classical boundary layer type of problem, right? You look at the coupling functions, right? You say that at the flame sheet they must all go to 0. Okay. And the coupling functions, we don't say that the second derivative is 0, but rather the product YO, YF, because the product of those two things are 0. Okay? But of course, they will fail at the reaction zone, of course. That's why the temperature profiles are discontinuous. All right? So once then from stretching, you will go, the next step is to take the reaction zone and stretch. Okay? When you stretch, the second derivative comes right back, and then you can show that the temperature profile is now going to look like this. Curvature in between. Right. Okay. And of course, the fuel profile will not be straight lines. Instead, it will curve around. The oxygen profile will curve around as well. Okay. Yeah.
What's the typical meaning of scalar dissipation?
It is a characteristic resonance time. The units of the scalar dissipation rate is 1/seconds. Okay, so it plays the same role as the strain rate. Okay, in fact, there are a relationship between the strain rate and the scalar dissipation rate. Okay. Okay, so I think we can continue on. Okay, all right. So that's the outer structure. And again, these are okay, maybe it didn't, okay. Oh, yeah, okay, all right, there you go. Okay, so you can see that, and how do I get this? Okay, if you look at the temperature profile in the region Z less than ZST, okay, which is in this region, all right, there's no oxygen. Okay, so you take this cup. Okay, you take a similar coupling function with O2, right? And you solve that, and you can get this. You get this temperature profile on this side. Okay, and on this side, Z greater than ZST. There's no Z greater than ZST. I'm sorry, I said the opposite, right? Okay, I'm sorry. Z less than ZST. In this region, there's no fuel, right? So therefore, this particular expression here is obtained by integration of that. Okay, right? Okay. Now on this side, there's no as Z greater than ZST, there's no oxygen. All right. So therefore, you get that from integrating an equivalent equation with YO2. Okay. So the point is you can construct these temperature fields. Okay. This is a classical Burke-Schumann structure, right? Okay. So that's the outer structure. Now we have constructed the outer structure. Now, of course, that doesn't give you critical conditions. We have not even looked at chemistry, with the reaction rates. All right. So the next step is to try to look at, based on the previous quiz, try to analyze the structure of the reaction zone. To analyze the structure of the reaction zone, okay. Okay. So this is that. So again, that's the reaction rate omega. Okay, for the one-step reaction written in that form, okay? So that's the, right, so now you take this omega, the reaction rate, okay, put it into that expression over there. Okay, so you get this, that's the equation that results. This is obtained by taking this, taking this omega, putting it over here, the reaction rate. So that's the equation, right? Now to analyze the structure of the reaction zone, we have to perturb the temperature, okay, around the adiabatic temperature TST, okay, and also from the coupling relationship, get the mass fraction of the fuel and the mass fraction of oxygen in this region, okay, right? Okay, so that's the energy conservation equation, and okay, yeah, and then those are the stretching. So this is the temperature, is the adiabatic temperature minus a small correction. Okay, you can see that this quantity epsilon is small. That's the so this is so essentially what we're trying to do is you have this thin reaction zone. So there's a thin, I'm just going to make that wide. There's a thin reaction zone. Okay, this is the outer structure. Comes on like this. Okay, so we're trying to we're going to try to get this temperature profile here, right? If you look at the profile of the fuel profile, the dotted lines are the outer structure. So we're going to try to get this. This is going to be the profile of the fuel. This is the profile of O2. And try to get this. So this is Y. This is Y. YF. Sorry. This is YO2. Okay. And this is the temperature profile. Okay. So. So this quantity here, epsilon TST minus TU, this one is a measure of the difference between the adiabatic temperature. That's that measure over there. Okay, that's epsilon times TST minus TU times Y. Okay. So those are the perturbations. All right. So that's the temperature is given by that perturbation. And once you write the temperature, once you write the perturbation for temperature, we can go back to these coupling relationships, okay, between the fuel. Okay, I didn't write down the coupling relationship. From the coupling relationship, so this will be the mass fraction of the fuel, okay, that obtained from coupling relations, and this is the mass fraction of oxygen. What's not shown here is the stretching for the independent variable, this C. So the independent variable C is Z minus ZST or epsilon. Okay. So that's the independent variable. All right. And these are the. So this is so the point is that you define that as the stretched independent variable. Okay. Because Z is close to ZST in the reaction zone, epsilon is small, that's of order unity. And then you expand the temperature about the adiabatic temperature. You introduce that. So this is the expansion that is introduced, okay? And once you introduce the expansion, you can look at the coupling functions between the fuel and the temperature, oxygen and the temperature, to obtain these relationships. So these two relations are obtained from the coupling relationships. And these two things are postulated, okay, right? Okay, so once you do that, okay, so now let's look at it. Okay, again, this is another typo. Sorry, there are many typos here. This is times, okay, that's exponential E over RT times this E. So this is times. It's not equal to, but rather it's a times. So again, typically what's done here is the classical expansion that you simply write 1 over T, okay? Use that expression, so you can write that as 1 over TST, okay? Times 1 minus epsilon times TST minus TU times Y over TST, okay? To the minus 1. You can do a classical, okay? You can write it that way. That so essentially this is what is done here. You can see, so therefore you get two terms, or you get a 1 over TST, right? You can multiply the whole thing by E over RT. So you get this. So E minus E over RT is exponential of that times the exponential of that. Where again, the Z is now is a Lavish number that appears again. Okay, right? Okay, so now, if you introduce all that into, so if you introduced these expansions into this differential equation, you get this equation. So this is the structure. So this is the equation that determines, that gives you the structure of the reaction zone. Okay, so, so that's the equation for Y, which is of course the perturbation. All right. Okay, now here you can see there's a Damn-Coulomb number that appears. So dA is a Damn-Coulomb number that's given by this equation. All right. Now what? Okay, now again that's the same equation again. That's just the same thing. Okay, it's rewritten here. Now what Norbert Peters has done is define new variable z. Okay, z in this form. Okay, this is just a simply rewriting this equation. Okay, if you define a new variable z, which is related to y and c in this form, okay, and introduce a quantity gamma like this and a beta like this, okay, then it turns out that so this equation can be transformed to this equation. And the motivation for doing this is because this is an equation which was analyzed by Linian. Okay, and it turns out solutions are available for this equation. Linian has obtained solutions to the equation. So if you take this out of equation, make this transformation, now you get this. So now it's possible to get solutions to this exist. Now there's a very important. So I'm going to look at this equation a little bit more in detail. Okay, now here, now you can see that we have not selected the value of epsilon. Okay, we have not said what epsilon should be. Okay, so there are two selections. I mean, since you can either select epsilon such that epsilon times beta is 1. Okay, so you remember the beta is related to the Zeldovich number, right? So if you select epsilon such that this is 1, that is large activation energy asymptotics. Okay, or alternatively, you can select epsilon such that this is 1. So that is equivalent to a large Damn-Coulomb number asymptotics. So this is large Damn-Coulomb number asymptotics, and that's large activation energy asymptotics. But it turns out, just like the homogeneous reactor problem we looked at, this problem is large Damn-Coulomb number as well as large activation energies. Therefore, it's a distinguished limit. Okay. Right. So now, so that's what I said here. There's evidence that two ways to define expansion parameter, either by this or by that. Okay. This is called the large activation energy expansion. This is a large Damn-Coulomb number expansion. Now both are equivalent if both are equivalent. If you look at the so-called distinguished limit, so you can obtain that. For example, if you cube this, if you take the cube of that beta cubed epsilon cubed, and you take the ratio of these two quantities, okay, that's 1. Okay. Now, so now you can define that this delta, which is obtained by this rate, if you assume that delta is order 1, okay, so this becomes a distinguished limit, okay, of large activation energy as well as large Damn-Coulomb number, right? Okay. Okay. I think, are we running out of time or yeah? Right. So, where's the what? Yeah. Are we over or? Okay. Okay. All right. So now this is so then you get an equation of this type. Okay. So now so what we have done here is assume. Okay. Now this is just to do a similar to what Linian has done. We assume that we define epsilon as 1 over this quantity. Okay. The epsilon is this. You define it that way. Okay. Then you can get this resulting equation. Now the boundary conditions to these equations are obtained from matching. These are matching conditions, right? And then you get, now it turns out that so this is the differential equation, these are the matching conditions. If you analyze this differential equation, it is possible, then you get the classical C-shaped curve, okay? And from the C-shaped curve, one can get, and this is basically linear, so this is, this particular expression for the Damn-Coulomb number actually comes from Linian's work, okay? So you get that. So that's the Damn-Coulomb number at extinction, or obtained at the turning point. Okay. Okay. So now I'm pretty much done now. Okay. That's the. Now I want to show a few things. Okay. And I can some profiles, for example. Now here, this is the temperature profile. Okay. This, of course, this is for the large Damn-Coulomb number. So as the Damn-Coulomb number is decreased, you can see that the temperature profile looks like this. Okay. So that's the extinction point. You can see so this was a large Damn-Coulomb number, complete consumption of fuel. And it turns out one of the unsatisfactory aspects of Lignan's of this particular analysis is that it predicts leakage of fuel. But it turns out that in real flames, there's leakage of oxygen, whereas the leakage of fuel, whereas this particular analysis predicts leakages of fuel. Right. Okay, now one can go back. So remember that we have this dam coral number. We have defined this dam coral number, okay? And then you have the number, that is the delta. And remember that this delta was actually 1 minus gamma. If you put all that, from here you can see you can get the scalar dissipation rate. If you put all that together, so this is a prediction. So this is the scale. So that's the final result. So this gives the scalar dissipation rate at extinction, okay, for the flame, right? So you can see the scalar. So that's the extinction scalar. So that's the quenching scalar dissipation rate, right? Okay. I think that's pretty much what I want to say. I mean, so that's the quenching scalar dissipation rate. Okay. Again, he talks about auto-ignition, but of course we are not talking about auto-ignition. Okay, finally, I want to point out that for methane flames, or in fact for many hydrocarbon flames, this activation energy asymptotic analysis of Lignan as well as Peters predicts fuel leakage to the flame, whereas in reality, in real flames, it's the oxygen leakage that takes place. Other than that's the only unsatisfactory aspect of this analysis. Yeah. Okay, I have another. I want to talk about maybe later on. I want to talk about the application of this activation energy asymptotic analysis to predict the chemical inhibition of flames. But I think I'm going to do that later on. Okay. Are there any questions or no questions? Okay. Yeah. Okay. Yeah.
Flow is incompressible. Flow is incompressible.
Yeah.
Suppose flow is compressible, high speed flow. What will be the changes we can make to this things?
I mean, these analyses strictly restricted to low-speed flames. Okay, so therefore we do not consider compressibility effects, right? The compressibility effect is a completely no. This does not apply if the flow is compressible. No. Then you have to look at the momentum conservation equation as well. So this particular analysis, because of low-speed flow, automatically as a consequence of low-speed flow, is that pressure is constant everywhere, right?
Yeah.
Okay. So then, of course, if you have a compressible flow, then one has to couple the momentum equation also along with this. That's a completely different analysis altogether. Yeah.
Okay. Yes, I have come across some papers from Stanford turbulence research recently that corrected this theory. Compressibility in terms of a power law scaling factor. Probably I can share you the papers. I could understand how that correction is understood in this philosophy.
No, I'm sorry, I didn't follow your question at all because there's echo. There's too much echo, and I cannot understand.
This flamelet theory, when we extend it to supersonic flames or supersonic flow, can be for the compressibility.
No, sorry, I cannot follow. I think maybe you should not use the mic. Yeah, maybe you don't want to use the mic because it's a. Yeah, because I cannot hear the mic. Okay, it says you will talk. So mic now.